Welcome to the Spectral Geometry in the Cloud seminar. And today we have the pleasure of having Victor Ivrii, who will speak about pointwise spectral asymptotics out of the diagonal. So the floor is yours.
Okay. So we consider Schwarz kernel of the spectral projector, and we want to establish semi-classical spectral asymptotics. So when h goes to 0 of this thing, and we want it to be uniform with respect to x and y on the final, well, so it should work for both x not equal y and x equal y and x tends to y. While such asymptotics for each restriction to the diagonal, and especially for its trace, are well known, the out-of-diagonal asymptotics are much less explored, especially uniform ones. Our main tools, microlocal methods, improved successive approximations, and geometric optics methods. I want to just mention that we can get out of this classical asymptotics. So when h is, say, h1 is fixed and tau goes to infinity. So let us start from asymptotics when x and y, well, are disjoint from the boundary. Sharp classical asymptotics for elliptic operators are well known. Hermander and Q could be traced to Levitan and Evakumovich. It's Hermander is mid-60s, Levitan is early 50s, Evakumovich is mid-50s. I could not find asymptotics of x, y, tau, despite it could be easily derived by the method Fourier integral operators combined with tau Balancier. So let's start from x and y disjoint from the boundary. So let A be self-adjoint scalar, pseudo-differential operator with smooth symbol, which is psi-macrohyperbolic on the energy level tau. So that means that when A is tau, the gradient with respect to psi is not zero. And A is a small is a principal symbol of A. And also we assume that the surface is strongly convex. Then EHXY is equal to Weil expression. I explained to Y expression what it is, plus or capital of H1 minus D, where Weil expression would be given by this formula, by quite natural formula, and we call it Weil expression. Actually, in dimension 3 and larger, we can take A in point X or in Y or in between, does not really matter, but in dimension 2, we must take the midpoint. Otherwise, error would be larger. Or we will need a correction term. So, on the other hand, asymptotics near the boundary for second order elliptics are known from late Seeley and sharp one from myself. The semi-classical version would carry remainder estimate from Seeley h minus d, and here it is nu is a distance to the boundary. And for myself, it's hy minus d. While the trivial remainder estimate would be like this. The difference between -1/2 and -1 is crucial in one sense. -1/2 power is integrable if boundary is not very irregular, and -1 would have logarithmic divergence. So this was actually the very big problem when we tried to derive asymptotics for eigenvalue accounting function. So we consider that introduce two distances. One of them is distance from x to y, and the second y, it's from x to y plus distance from x to 0 and from y to 0. Actually, we don't need both of them. We can take any of them. And see, consider second order operator, elliptic self-adjoint scalar operator, and also with smooth coefficients. And we assume that it is hyperbolic, which would mean exactly this in this case, with either Dirichlet or Neumann boundary condition, and boundary will be smoothed. Then, if d greater than 3 or equals 3, then the same asymptotics holds with the remainder estimate, where the main part would be equals, while expression in the whole space from with point x, y, and here is tau, and here instead of x we take y, and y is reflected. Okay. Actually, it should be y here, tilde y, not tilde x. Only x, but tilde y. And for d greater equals 2, under one of the following assumptions, namely, distance is less than 1h, 1 over 3 plus delta, or it's greater than this, or the following inequality holds, this asymptotics would hold with correction term, which will be defined much, much later. Finally, if neither of these three conditions is fulfilled, then remainder estimate could be made a bit larger. According to my old theorems of 80s, theorem asymptotics, this asymptotics would hold in the coordinate system such that x1 is a distance from x to boundary in the following matrix. Such precision is needed for d equals 2 only. So in this case, there would be no correction term. Otherwise, we will need correction term. The leading term would be of this magnitude. In particular, it would be hy minus d when L is not too small. Observe that when d is 3, it would be 1/2. When d equals 2, it is 1/3. When d equals larger than 3, it would be less than 1/2. So it would decay faster for large d when L tends to 0. The correction term, on the other hand, would be of this magnitude. And this correction term would be really, really of this magnitude if we assume, for example, that the boundary is either convex or strongly concave. On the other hand, there is a trivial estimate in much more general settings, and this would be this one. Okay, now I need to explain certain things. So we have basically 3 different types of asymptotics. One of them is eigenvalue accounting function. Another is EH when x equals y. And the third one is when x is not equal y and uniform. The first one is easier, and it requires less restrictive condition. Second is also quite old and not and does not require many conditions. For example, it falls under proper definition of psi-macrohyperbolicity as for matrix operators. The third one, when x is not equal y, is much more difficult, and I will try to explain why. The original problem was to find the asymptotic of the number of eigenvalues, and after Hermann Weyl and Courant, who used variational methods, Kahneman suggested a completely different approach. A variant of this approach, called hyperbolic operator methods, was suggested by Boris Levitan and Avakubovich. In semi-classical setting, it was transformed by myself to Schrödinger operator methods when we don't need to consider wave operator, we can consider semi-classical Schrödinger operator, because on finite energy levels, it behaves much more like wave equation. So we consider propagator. Then UH would be given by this formula. And therefore, when x equals y, we would get this one. And if you integrate, you will get that formula, well, all very well-known formulas, when NH is eigenvalue counting function. Then we want to construct one of the left-hand expressions by method of partial differential equations, and recover the corresponding expression EH when x is not y, or EH was xy, or n capital H. Usually we cannot construct those precisely and only on rather short time intervals. And then we recover only asymptotics, not precise equations, using Tauberian theorems. So we call these methods Tauberian methods. Usually in Tauberian theorems, one assumes that the function of tau is monotone, which is the case when x equals y or m tau, but not when x is not y. However, proof of Tauberian theorem consists of two parts. Knowing approximately the left-hand expression on the interval from minus t to t, and using monotonicity, we prove the following estimate: that if you increase tau by t minus 1h, then the increment of EH would be not given by this form. Okay, sorry, here should be t minus 1. Not t. And knowing approximately the left-hand expression on the interval from minus t to t, and using this estimate, we recover EX tau with this remainder estimate. Yes. Consider now xy, which are not equal. We already know that they under pretty general assumptions, which we will discuss later. In particular, in framework theorem 2, estimate 14 holds with a small constant t, like this one. But then we have the same estimate, not necessarily for x equals y, but for x may be disjoint from y. And then we can even take not this one, but we would have this estimate, it would follow from it. And then the due to Tauberian methods, we would get the following estimate, where T means what a Tauberian. This T tells me on what interval we know it, and this is called Tauberian expression. Now we need, what I'm saying that Tauberian theorem consists of two parts, deriving estimate like this, and then deriving asymptotics like that. And estimate like this, we derive first from not using monotonicity, but on the second step, monotonicity is not needed. Now we need to calculate Tauberian expression. Assume first that we are away from the boundary. Then for small constant t, we can construct UH as an oscillating integral, and we can construct Tauberian expression. And this construct for small time, for small constant time, is well known and was used to calculate this asymptotics, but it could be applied to this case as well, even as d equals 2 or without strong convexity assumption. However, then the final result could be quite complicated because it would include some unknown phase function, and only under strong convexity assumptions or similar like this, it could be simplified to expression which was given before. Construction of propagator is much more complicated close to the boundary, because during generalized billiard race, almost tangent to the boundary. And those who were active in 70s or in 80s knew that this was the real obstacle to proving Weil conjecture for domains. In the full generality, this task was never achieved, even for Laplacian. So how in 1979 and later I managed to deal with this? By propagator methods, under probabilistic condition, I proved the following, that you can take cutoff on the interval epsilon1, or you can take cutoff on the interval a bit larger than h, and then it would be almost the same. Why? Because singularities go away from the diagonal. It is not true for EH, because a ray orthogonal to the boundary bounces back to X either the time T of magnitude distance to the boundary. But as I explained, this only rays which are almost tangent to the boundary are the problem, not the rays which are transversal to it. On the other hand, if T in this interval, we can construct Tauberian expression by methods of successive approximations, freezing coefficients at point y, and each next term acquires an extra factor t squared h minus 1. So when we freeze coefficients, we have constant coefficient operator, so we do this. Combining these 3 points, I got Tauberian expression for an h and e on the diagonal. To calculate Tauberian expression, we combine all these 3 methods, but in different ways. First of all, we decompose UH into 2 parts. One corresponds to free space and another corresponds to reflected waves. And then Tauberian expression consists of also 2 parts. So we need to calculate, and the first one is we know how to calculate. The second one should be calculated. In the general, this may be many generalized billiard rays with at least one reflection from the boundary from X to Y on this given energy level tau. However, all of them have the length L of x, not L naught, but Lx. So we can assume without generalities that boundary is given by x equals 0, and that one of the magnetic potential is 0, and that G1k equals delta 1k. We can always achieve this. Then make a local methods prove that actually we need to take T prime of the magnitude L. Further, local methods give us the following decomposition: that if we consider EXY, then we can add cutoff by X, pseudo differential, and by Y, and then take X equals Y. Under these conditions, and it would be a local uncertainty principle. And this condition would be necessary because basically rho can, if we don't have, let's say, toy model, in the general case, rho can change psi during trajectories. Combined with stubborn methods and strong macroballistic equality allows us to upgrade trivial estimate due to the following one. Because of cutoff. And if I take rho like this, then I would get O capital like this. When d greater than 4, when d equals 3, we have this one. And for L less than H1 minus 3, as d equals 2. In addition to this estimate, my local method allows to justify other methods. There are successive approximations. First, I explain successive approximation inside of domain. We need to consider this and rewrite for U plus minus equation like that. And we'll solve by successive approximation. Then, if I take A bar equals to A with symbol frozen at point Y, we will get like this. And therefore, we write successive approximation. And then iterating, we will get this formula. Well, and finally, we apply cutoff by Y to the right of 30, where Q is an operator with compactly supported symbol. After this cutoff, norms of the terms wouldn't exceed, well, doesn't matter, M is constant. But look at this. We add each time because the X and Y minus Y is of magnitude not exceeding T, but from Duhamel principle comes extra factor T, but we need to divide by H. So every next term acquires factor T squared over H. And then when T is less than 1/2 plus delta, we can ignore the remaining term. We did the proper cutoff of the norm, does not exceed, and it's explained. Since we need to consider T less than L, then we need to have this equality in this estimates, and then it was shown that just we do it simply solving one after another problems with constant with respect to Y symbols, with respect to X symbols. and do some calculations. But on the other hand, we know those things, I remind you. And then for d greater than 4, we are completely done. For d equals 3, there is a tiny gap like this between these assumptions and above restriction. And for d equals 2, the gap is really large. L is between those values. To deal with this, we need to improve successive approximation methods. Well, I remind you that inside of the bound of domain, we can use oscillator integrals, but this is for me just toy to understand how to deal in the case when there is a boundary. To improve this approach, we need to freeze symbol at point W. And to do this, let us observe that we have the following equations. And therefore, denoting introducing W and Z, we write like this, then we write successive, do again exactly like successive approximation methods, but because we take symbols in the middle, then instead of this factor, we gain this factor. This h does not matter, but here instead of t squared, we get t cube. So what we need this restriction. Calculations similar to those at the standard methods lead us to the main term, and to the second term acquiring an extra factor like this. So it would be hy minus down d under assumption even for d greater than 2. So for d greater than 3, there is no gap. Okay. And for d equals 2, gaps is now tiny, like this. And this would remain until the very end. We know this explaining how I was making standard successive approximation near the boundary. Basically, it was done in 80s. In this particular case, I don't so we write again the problem, fix the coefficients at point y, and do these calculations. And again, the same formulas, the very similar formulas, but there are actually two parametrices, G and G prime, when G works with the right-hand expression and G prime works with boundary conditions. And it basically repeats all these arguments. Iterating, we get these formulas.
Victor, I have a question for you.
Yeah.
When you say the word parametrices, what are you referring to? Are you referring to the very complicated ones of people like Taylor and Melrose and Eskin? Or what are you referring to?
Well, at the moment, I'm talking about parametrices for constant coefficients, Fourier transform, and that's all, nothing complicated. And finally, we making cutoff, justifying, and just explaining what it is. The only difference is that because I cannot take the half, the midpoint with respect to x1, which where x1, x0 is a boundary, I put here sigma. Sigma is the angle between boundary and incidence angle of the ray. And in this case, I do the same construction, but I need, in addition, also this condition. So when L is 1 to the tiny less than 1 h1 over 3, 1/3, or and also this condition holds. So ray is not too steep with respect to the boundary, that we can do successive approximations. So we get asymptotic series, and making lots of calculations, we basically arrive to the proposition. If all this holds, then we have these conditions. And for D, we need to be a bit more sophisticated. Now we need to study Hamiltonian billiards. And proposition 4. If we have these assumptions, and LA, then they exist a single generalized Hamiltonian billiard of the length, then there would be just one Hamiltonian billiard connecting n xy. It has exactly one reflection at end like this. Well, when I say from X to Y and from Y to X, it's actually a bit too different billiard. If there are magnetic potential. And this assumption is essential. Now we follow rather standard construction of a canal and amplitudes in the whole space, like in the book of Misha Shubin, and carefully analyze construction of those for the reflected wave. Okay, this is just like this. I don't want to load you with all these estimates, but important thing is that if we consider formal construction, then basically what we have if lambda is not 0 and lambda is a derivative, then we gain from each term we gain factor h minus 1/3. Okay, we gain some factor like L cubed divided by h. So we again need some conditions. Then this is basically how it's can be done either when there is no boundary or we are steep to the boundary. Simply here we are much more careful to consider all the terms to deal it's with much precision, because otherwise we would not get uniform estimates. And then we arrive to the following macro-local results. Again, that U1 capital, which is formal series, actually gives us good approximation to the real solution. And then corresponding Taubman expression could be simplified. And then we consider this different oscillatory integrals. Well, case d equals 2 is a bit more complicated, so we need to deal with the fact that we cannot take x equals y. We need to take x1 plus. We cannot take midpoint between xy because of x1 and is positive and y1 is positive, but minus y1 will be negative, and x1 minus y1 would be negative. So we need to do it a more sophisticated way. And we arrive to expression, to this expression. And now the theorems 1 and 2 follow from what we have proved, covering different zones. And it would be nice to get estimate h minus 1 for d equals 2 without this tiny gap. And actually it can be done under assuming, for example, that some flatness, but it is not worth of our efforts. For Schrödinger operator, we can get a psi-macromobility assumption by rescaling. Then for d greater than 3, we have a remainder estimate like this. And as d equals 2, remainder estimate would be like n minus 4/3. And we would like to extend it to, but if d equals 2 and x away from boundary, we can get a remainder estimate under this macromobility condition, but with a correction, some correction term. The reason is that v equals tau would be kind of some soft boundary, and there are up to 2 trajectories from x to y. One of them is on the length x minus y, and another touches x y. We would like to extend it to larger value of L, but so far I did not think about this. Basically, there is simpler version of the proof is proven here, but I will upload a bit new version with some improvements in a few days, maybe in early August. And then there is a second case when we consider without psi-macromobility conditions inside of domain. To combine both results would be a very difficult task, and I'm not going to do this, with a very simple reason. Then the geometry, you see, Vx equals tau is soft boundary, then there is another hard boundary, and to combine them, it means some complicated study of behavior of billiards, which can reflect from both boundaries. And that's all.
Thank you very much, Victor, for this talk. We have time for questions now. If you have questions, you can either ask them in chat or unmute yourself.
I have a question.
Yeah, go on, Alex.
I have a question about what what do you mean by uniform estimates away from the diagonal? Now, in the context of a Laplace-Beltrami operator on a compact manifold where everything is smooth, everything is nice, etc., you actually expect the kernel of the spectral projector to decay away from the diagonal as it would for the flat Laplacian, like the power of the distance to the, I don't know if it's n+1 or n-1.
Yes, and there is yes. And there are reference to paper of Safarov and book of Vassiliev Safarov, but it is when x and y are fixed. However, it is when x and y are fixed, or x, y stay away from one another. But if we allow, but I didn't say away from the diagonal. I'm saying not on the diagonal.
Yes.
Yeah, the difference is that we want a result which would be provide uniformly made estimates for on the diagonal and when x and y tend and say when y tends to x.
Okay, I think there's a recent paper by Kanzani and Hanin on related things. They have a narrow term. So the main parts, right, is this parametrics with frozen coefficients and just a Fourier transform, as you said, and the remainder is an h factor times the size of this thing, and this happens at every scale for x and y.
Okay, h which thing times a which thing?
So say if the actual kernel, say in the flat case, behaves like h to the minus n times distance between x and y plus 1
Okay,
to the power k.
Okay, are we talking about case with a boundary or without boundary?
Huh? Sorry, what?
Are we talking domain with a boundary or manifold without boundary?
No. I'm still talking. Sorry, about the case of a smooth boundary-less Riemannian manifold.
Well, as I explained, this is a relatively easy case because basically you can make a whole construction using oscillator integrals.
Sure.
The only problem is that you want to simplify it.
Yes.
Simplify the result.
Yeah.
The main topic here was theorem 2, when we are looking for the domain with a boundary and the x and y are close to the boundary. And
sure.
what is a real complicated case when x and y are quite far away from one another. So that means that rays from x to y is is almost tangent to the boundary.
Mm-hmm.
This is and in this case, when x and y are close to the boundary, when we say ray, it does not mean just one ray, because there could be tons of rays going from x to y on the same energy level.
Mm-hmm. So you don't expect any, or maybe a very a much weaker kind of decay a spatial decay in the kernel? Or do you know that you have no decay?
No. There is power decay of the kernel when well, actually it's not decay. What happens when x goes to y, then there would be some estimate, and this estimate is just precise.
Mm-hmm.
So it would be h say in case d equals 2, which is the most complicated case, it would be behaves like h minus 1/2 and the distance minus 3/2.
Uh-huh.
When d equals h, then the distance equals h. We just take h instead of distance and we get h minus 2.
Okay.
Yeah, so basically, but we need to have, we want to have remainder estimate, h minus 1. And again, as I explained, d equals 2, the most complicated case, because decay away from the diagonal is the slowest.
Uh-huh. Okay. Thanks.
Thanks, Alex, for the question and the remarks. Before going on with another question, if there are some, there's a remark in chat from Lotfi Hermi, who remarks that there are pointwise estimates for the kernel away from the diagonal in Carlemann's work in the 20s. I don't know.
Yes, I have seen this remark. Yes. Well, again, I will look at Carleman work, but and should definitely reference to it. But again, it's probably not uniform, and Carleman, because Carleman invented Tauberen method, but hyperbolic operator method was invented much later. So this variant of so his result never were sharp.
Thanks, Lotfi, for the comment. Does anyone else have any question for Victor?
I have a question.
Go on, Steve.
Hey, Victor, can you hear me?
Yeah, sure.
Okay, so suppose that we take the Neumann boundary conditions.
Yes.
And then we put both variables just on the boundary. Right? In fact, let's just put them at the diagonal. So we have
if you put them on diagonal on the boundary, you will have the normal while expression doubled.
Well, that's the question. So what do you have in your work a proof that you just get like if you take the wave group, let's say the dual thing, and you put both points on the boundary at the diagonal, then it should be a Lagrangian distribution. It should just be a classical oscillatory integral. Okay,
to make things like this, yes, it would be, actually it was proven like in 80s.
By whom?
By myself. Look at look at this. My idea was very simple. If you consider not the case when there is no boundary, then when x equals y, you get a Lagrangian distribution.
Yeah, of course.
On the other hand, when when there is a boundary, then situation slightly changes.
No, I understand. I mean,
yes, okay, but in particular, when you
slow down, it's obvious you have an isolated singularity at t equals 0. It's obvious, but how do you know it's a Lagrangian singularity?
It's proven.
Where?
Okay, basically you can for semi-classical version of it, It's proven in my book.
Where exactly?
Okay, I will need to look in the, depending on what book you are talking. I may be in book 78. But it also may be, you can look at book of 98 in chapter 5, or in book, the latest book in chapter 7.
Do you use the parametrics method to prove it or not?
The proof is the following. You study propagation of singularities. Then, when you study propagation of singularities, you discover that this thing are negligible. Well, actually, my answer is would be correct if you cut off normal rays. But normal rays would not prevent us
There's
from.
there's no need to cut them off. We're on
No, yeah, you're right. You're right. Okay. And the idea is that when you prove this, then you can when you say that all the singularities lie in t less than h to the power 1 minus delta.
No, for sure. There's no problem about isolation of the singularity.
No. Wait, please. Then when you can make construction by freezing coefficients in using parametrices for frozen coefficients in iterating them.
You know, I've tried this kind of method. Do you know the work of the physicist Roger Balian and
No,
Bloch?
I don't.
From 1972. It's a very nice paper, and I think they do what you call successive approximation. I do believe that they do exactly the same thing. In fact, I'm not so sure what you mean by successive approximation, but they basically expand in a geometric series. You know, if you
no, it is not. What I mean, I explain. You freeze coefficients. So then you have coefficient and perturbation. Then you just write series of successive approximations.
It's the same idea. No, it's the same exact idea. It's expressing the Neumann or Dirichlet-Laplace operator in terms of the Euclidean ambient one, on the ambient space. And then you make a series of successive approximations. It's exactly the same method. It's the same as Poincaré's method in the case of harmonic things. Balian and Bloch basically did the same type of thing, but you don't get the same convergence theorem that Poincaré proved for the harmonic case.
Okay, but the trouble is that physicists never were proving where it is.
It's formal, but very rigorous up to a certain formal level.
Yes.
But it's very
but this is justified what I'm talking about.
No, so is this. Later I wrote a paper to justify using the Melrose-Jostron propagation of singularities.
Okay, but look, when unfortunately I did not know your paper in '79.
You mean Balian and Bloch? Yeah, I think you'd like Balian and Bloch paper. It's a very, very nice paper.
Maybe, yeah. If you send me a reference, I would be very.
Okay, I will.
Thanks.
Thank you very much, Steve, for this discussion and the references. Do we have other questions for Victor? We might have time for another one. All right. If not, thank you very much, Victor, for the talk today. We will take a break for the next 3 weeks, a small summer break, and restart on August 23rd, on Monday, August 23rd, with a talk by Wenkai Liu. Until then, I wish all of you good summer holidays, and I wish myself a good summer holidays. Have a good time.